Right. Okay, so the goal is to prove the theorem. There exists a formula representing the exponentiation function, namely representing its graph, so it's going to be a three-variable formula. So because there were questions on the notion of representability, maybe I'll just make a few remarks about representability. So every formula from the definition, every formula A with k free variables represents exactly one relation. So it represents some relation and it uniquely determines it. It's kind of immediate from the definition. Represents exactly one relation R, which is a k relation. And then a k plus 1-ary relation. What does it mean to represent a function and a partial function? Well, an R in n to the k plus 1 represents a partial function. Sorry, they're not representative. Formulas represent relations. So is the graph of a partial function from n to the k to n, if and only if for all n1 to nk there exists at most one m such that n1 to nk and m are in the relation. And it represents a total function if and only if there exists exactly one. Okay. So does that clarify, hopefully? Representing partial, a formula represents exactly one relation, and a relation is the graph of a partial function if and only if every k tuple has at most one possible value, and is a total function if and only if for every tuple there's exactly one value. Yes.
I just wanted to make sure. Actually, as I understand it, this definition works well for partial functions as well.
Yeah.
Yes.
Yes. Right. Okay. So we want to show that exponentiation is representable. It's not straightforward. So we're going to first show a couple of very simple functions are representable, and then we're going to need a big, powerful result, which is called Gödel's beta-lemma. And once we've got that, then this theorem will follow quite straightforward. I mean, with a bit of work, but there's a nice idea behind that. I'm going to leave the proof of the beta-lemma till later. I mean, we'll do that today, but I'll use it first so we can see how it's applied, and then we'll do the proof of the beta-lemma, which is a very clever contribution of Gödel. Okay, so we want to start by representing some very simple partial functions, or total functions. So the first lemma is that the modulo function is representable by a delta zero formula. Lemma, partial function of x, y mapped to x modulo y, by which I mean the remainder you get when you divide x by y is representable by a 3 argument delta 0 formula, and we'll just say delta 0 representable. Why is it a partial function? Yeah, so it's defined if and only if y is greater than 0. So we just need a 3 argument delta 0 formula, and in this case, we simply, so I'm going to call this formula rem, and we can just, it's really easy to find such a formula. So when is z the remainder of x divided by y? Well, let's see if I've got this right. Yeah, it does force y to be greater than 0 because, so z needs to be less than y, and which forces y to be greater than 0, and there needs to exist some w such that x equals y times w plus z. That's saying that z is the remainder. Okay, these two things. However, to make it a delta 0 formula, we need to bound the existential quantifier, but it's obvious in this case that we can bound the existential quantifier by, I seem to have got it being less than or equal to x in this case. Yeah, it's obvious. Very straightforward. Okay, so we'll go to another very simple function. And so again, the lemma is going to be, so it's a total function this time, and again, the lemma is going to be that it's delta 0 representable. So lemma, the function pxy defined to be a half x plus y times x plus y plus 1 plus x is delta 0 represented. Why this function? Does somebody recognize this?
Yes.
Yeah, the pairing function.
Yeah.
So it's the function that counts up diagonals. If this is x here and y here, 0, 1, 2, 3, 0, 1, 2, 3. So this is 0, then which way around does it go? Here we have 1, 2, 3. So we just count along the diagonals. So it's a bijection between n squared and n, the natural numbers squared and n, 4, 5, 6, 7, 8, 9, and so on. Okay. So we're using p for the function. And so I'm always going to have this convention that the formulas I'm going to give names with capital letters. So we know we're distinguishing between the formulas representing functions and the functions. So the formula here I'm going to call it pair, and well, it's almost obvious because this part is just simply a term, but we've got the multiplication by a half. So of course we can do that by using a 2 times somewhere in the formula. Or we could say 2 times in many ways. We could use s of 0 times, or we can just have something plus itself. So for me, the easy way to say this is there exists some W such that W plus W is equal to x plus y times x plus y plus 1 and equals W plus x. Okay. And now with this machinery to hand, though we don't actually need it directly for this, but we're going to use it. So this is a warm up just for how we represent things. And once again, yes. What have I failed to do here? This is not a delta zero formula.
Maybe bound.
Yeah, so we need to bound the W. It does have a bound in the note. So we can clearly give W a bound of Z here, because for this to be true, W needs to be less than or equal to Z. Yeah, so if this is W less than or equal to Z, there we go. Anyway, so these are some examples of delta zero formulas, and we've seen simple uses of them. So we're going to use these functions later, but I think we might not use them until we prove the beta-lemma, which, as I said, I'm going to postpone the proof and apply it first, but the next thing to do is to state this beta-lemma. So this is as I've said a few times, one of Gödel's very nice contributions in his paper. This lemma, and it's known as one of the gems of the paper, Gödel's beta-lemma, as it's called. And it's called the beta-lemma because what it says is there exists a binary function beta which we're not going to define. We will later define it explicitly, but to begin with, we're just going to say what properties we need it to satisfy, because it's quite tricky to define it explicitly. It's then going to be delta zero representable. So the beta-lemma says there is some delta zero representable binary function, a total function, so two argument function, beta, satisfying some properties. So I'll just state it and then I'll say what it means. So for every k, natural number greater than or equal to 0, and sequence of natural numbers of length k, so let's call them n0, n1 up to nk minus 1. There exists some natural number s such that we apply beta to s and any I less than k, we get back ni for all. So this is true for all I strictly less than k. And moreover, s to all the numbers n0 up to nk. Okay. So s is not too small. So the way to understand this is we're giving ourselves a way of representing finite sequences, of encoding finite sequences via a delta zero formula. And the delta zero formula represents the function beta that allows us to decode a numerical representation of a finite sequence. So the property of beta is for any length of a sequence, k, and for any sequence of that length, there exists some number s, the code for the sequence, such that beta, if given s and a position in the sequence as arguments, will extract the number in that position or return the number in that position from the sequence. And moreover, the code for a sequence, this is going to be useful. The code for a sequence is always at least as great as all the numbers at least as large as all the numbers in the sequence. Okay. So yeah, it looks quite innocent. All we're doing is encoding sequences as natural numbers. And you may think to yourselves, oh, I've seen lots of ways of encoding sequences as natural numbers before. So a common way of encoding sequences as natural numbers is to use prime factorizations. So if you've got some sequence of numbers, you take this as a power of 2, this is a power of 3, the next one is a power of 5, and so on, and then you multiply all the powers of the primes together, and that gives you a number that encodes the sequence. What's the problem with that for us? So we can't encode a sequence that way in our language, not yet anyway.
Not yet, because
we don't have exponentiation. So actually, if we get exponentiation, we can encode sequences that way, but at the moment we can't. And the point is this: we can define with a delta zero formula that avoids exponentiation. Just to say, there's another very nice encoding of sequences that one sees that I think I used in the computability theory course, where you use binary representations of numbers and do some sort of clever arrangement of the binary representation. But once again, in order to do that encoding that you may be familiar with, you need to use 2 to the power of function. So and we don't have that. So the point is, this we're going to be able to do with a delta zero formula. Right, so I think as I've said, I'm going to postpone the proof of this and first do the application. So the application is going to be proving that the exponentiation function is definable. I think we'll do that, then we'll have the break, and then we'll do the proof of beta-lemma. And that means, although we had a late break last time, it means we're going to have an early break, because it seems sensible to put the break in that position. So the application, we're going to prove that the exponentiation function is definable by a sigma 1 formula. So far, everything has been definable by delta zero formulas, including the beta function. Okay, so proof that x, y, the x to the function, the exponentiation function is sigma 1 definable. So we need to define a formula x with 3 variables, x, y, z, that is true if and only if z equals x to the power of y. Okay, that's what. So I'm simply going to give you the formula. So it is, there exists a U such that G beta of U01 so G beta here is by a formula G beta, so this is the delta zero formula that represents the beta function x, y of z, all right? So this is saying beta of U0 equals 1. And so we're going to have U is going to be used everywhere here. For all I less than y, there exists an R less than equal to U, such that G beta of UIR and G beta of UI plus 1 R times X Z. Okay, so that's it. The way to think of it is to notice, well, before actually going into the meaning, notice that it is indeed a sigma 1 formula because we have an unbounded existential quantification on the outside, and then everything inside involves propositional connectives, bounded quantifiers, and the G beta is the delta zero formula because the beta function is delta zero representable. Okay, so this is indeed a sigma 1 formula. So the way to think of it is we want to say that Z is x to the power of y. So U is going to be the code for the sequence of numbers that is of length Z plus 1. That is the sequence, sorry, not Z plus 1, is of length Y plus 1. There's the sequence 1, which is x to the power of 0, x, that's x to the power of 1, x squared, x to the power of 2, all the way up to x to the y, so x to the power of y. So we want U to be the encoding of this sequence. So the 0th position in U needs to be 1, and that's what this says. In the 0th position in U, using the beta function to extract the 0th position is 1. Then for every index I for a place in the sequence apart from the last one, the next position in the sequence is obtained by multiplying the previous version by x. So that's what this says. For all I strictly less than y, we need to say the position that the value that's at position I plus 1 in the sequence is x times the value that's at position I in the sequence. How can we get that value at position I? Because we've just got a formula, we need to put a quantifier to get it. So there exists an R, but we need to bound it this internal part needs to be delta 0 in order for this to be sigma 1. But we can bound this by U because of this condition here. Okay. So there exists an R less than or equal to U is good enough because it's some. So then there exists an R which is the value at position I in the sequence, and it holds then that the value at position I plus 1 is x times R. All right. And lastly, the result at position Y Well, that needs to be, we need Z to be that because that's going, these two conditions force this to be x to the power of y, and that Z, yeah, that needs to be the Z that we get. Okay, so it's not actually so hard. It's a really nice idea, but the idea is code things up as sequences, and in order to be able to do that, you need to know that you can code sequences. And that's what beta-lemma gives us. And yeah, so I was suggesting having a break, but it really seems a bit early for a break. So let's launch into the proof. So I'm sorry, if you feel hard done by, but I'm not even going to put it to the vote because it's 4-2, and I feel like I'd like to carry on. Are there any questions on this? Okay, good. So I want to keep the statement of the beta-lemma on the board, and then I'm going to rub this. Rub Gödel's nice formula off. Actually, when I stated the beta-lemma, I said it's hard to define the beta function, the beta formula, so we were postponing it. It's not actually that hard to define. What's difficult is to prove that it works. So let's define the beta function. So the proof of the beta-lemma. So we're simply going to say beta is the function that takes an S, the encoding of the sequence, and an index, the position, the index that we want to extract that element from the sequence, and it's going to give us back a modulo I plus 1 times m, and then 1 added to all of that, where a and m are the unique numbers such that pairing of a and m equals s. In other words, S is the encoding of a pair, AM, for which this relation holds. It says, let's say that again. Beta says, interpret S as a S encodes a pair, every number encodes a pair, extract the first and second component A and M, and it needs to be the case that the beta is then defined to be A modulo this. Okay? And that is the beta function. And this is easily represented by the delta zero formula, because we encoded the pair function. We showed that the pairing and modulo function were represented by delta zero formulas. So this is represented by the delta zero formula. So we need to say when Z is in this relation with, satisfies this property with respect to S and I. So this holds if and only if there exists an A and there exists an M such that S is the pairing of A and M, and then z, the value of the beta function, needs to be the remainder of this. Sorry, did I call it rem before? Yeah. So the remainder of a when divided by I plus 1 times n with 1 added to that whole value, the z. Okay, so we want this formula, except once again it's supposed to be delta 0 representable, so once again we need to bound the quantifiers. But now a and m are components of a pair, and the pairing function I gave also enjoys this property that the components of a pair are less than equal to the code of the pair itself. So we can always bound these. We can always bound these quantifiers by s. Okay. So that's the beta function. Not so hard to give the function, but we need to prove that it enjoys the right properties here. So for every length of sequence, for all the k components of a sequence, the value of the beta function will, there exists some number encoding the sequence such that the beta function extracts those values for those indices. Okay, so we need to show, it remains to show that beta, so let's put it up here. We need to show beta has the right properties. And for this, I think, so we're still early for the break, but still, this is the part that it really is better to start after the break. It's going to be a short hour next time. It's not going to take it's not going to take very long to do it, but still it'll take longer than the time we've got before the break now. So I should postpone that. So if you want to, over the break, you can try to think for yourselves about why this function enjoys this kind of property, why this is an appropriate way of coding the sequence. Good. So by the clock on the back wall, it's 7 minutes to. So we'll start at 8 minutes past. Okay. Are there any questions? Okay. Right. So we've got the beta function. We want to show that it has the right properties. So in other words, I obviously can't keep everything on the board. So let's just remember that we need to show for every length of sequence that there exists some number that encodes the sequence in such a way that this function successfully decodes the sequence, which we find explicitly here. And we'll probably have to rub that function off. So what we're going to use is one of the oldest results in mathematics.
The Chinese Remainder Theorem.
It is indeed the Chinese Remainder Theorem. Don't know, do you do it at high school? The Chinese Remainder Theorem, or you must do it somewhere. Algebra 2. Okay. Anyway, let's just call it CRT, the Chinese Remainder Theorem. So the version we need, which I guess is standard, is if we've got k numbers, which I'm going to call m0 to mk minus 1, it's a pairwise coprime. So take any two of them, and there's no divisor in common. We call them Tutsi or something, don't you? Is that right? Oh. What do you call it if two numbers are co-prime? Tuya.
Yes.
Okay. So each of them. There exists a unique A less than the product of all of them, such that A modulo mi equals ni for every I less than k. So if you've got a set of pairwise coprime numbers, then you can encode sequences bounded by those bounded placewise by those numbers in the coprime sequence in such a way that the elements of the sequence are extracted using modulo, using the modulo function. This is how we're extracting the numbers here. The only difference really is that we're starting with an arbitrary sequence of numbers n0 to nk minus 1, and we want to be able to use this kind of recipe. So what we have to do in order to apply the Chinese remainder theorem, we have to, from our arbitrary sequence, we have to manufacture a sequence of pairwise coprime numbers that are large enough that they contain the elements of the sequence we're given, and then we're done. Okay. So in our case, so can I guess I can fit it on one board if I use two panels. I'll remind you what the beta function is when we, let's maybe put it here, the beta function. So we've got beta Si is a mod I plus 1 times m plus 1, where PAM equals S. Okay, so let's give ourselves two panels, and so given some k and 0, our sequence of numbers that we want to encode, we want to manufacture a sequence of n's. So what we're going to do, we want to be able to apply the beta function to some a and m, and get it to work by the Chinese remainder theorem. So what we're going to do is define our m and our a. So m is simply the maximum. Take the maximum of k and all the numbers in the sequence and take its factorial. That's a huge number. We're going to define some even bigger numbers to get ourselves the bounds here. So I from 0 to k minus 1, we simply define mi to be I plus 1 times m plus 1. And we claim these numbers are pairwise coprime. The claim is that m0, mk minus 1 are pairwise coprime. So if they're not, then two of them have some common divisor, which might as well be prime. They have some prime common divisor. So suppose not, then we have that some prime p divides mi and p divides mj for some I not equal to j and prime number p. But if p divides both mi and mj, let's assume that mj is greater than mi without loss of generality. So then p divides mj minus mi. So in other words, p divides, so mj minus mi is j plus 1 times m plus 1 minus I plus 1 times m plus 1. So if you work that out, you get that p divides j minus I times m. A itself divides m. Why is that? So since there are just a few of us here, what?
Probably has to do with the factorial.
Yeah, it has to do with the factorial. So this is some number bigger than k factorial, and j and I are both index positions less than k. They're in the sequence length, so j minus I is less than k. So it certainly divides the factorial. Very good. So because j minus I is less than k. So if p divides this, but this also divides m, then p, p's a prime, it will divide one of the two factors here. And if it divides this one, it also divides m. So either way, p divides m. So if p divides m, so hence, p divides I plus 1 times m. So we started with p dividing mi, which is I plus 1 times m plus 1. Okay, and obviously it can't divide both I plus 1 times m and I plus 1 times m plus 1. But p divides I plus 1 times m plus 1, 2. That's contradiction, and the symbol I use for a contradiction is a hash. Like this, you can use whatever symbol you want. Okay, so the claim holds So that's that. These are all pairwise co-prime. So by the Chinese remainder theorem, we have that go up to k minus 1. There exists an A such that A modulo, well, and what it gives us is that A modulo mi, which is A modulo I plus 1 times m plus 1, I plus 1 times m plus 1 equals ni for all I from 1 to k minus 1. So for all I less than k. And that's exactly what we need, because so if we define S to be the pairing of A and M, and then we get that beta of S of I is exactly this, which is Ni for all I less than k. Okay. So anyway, it's a very nice argument to use this really ancient theorem to be able to do this in coding a sequence in a sufficiently nice way to be able to prove this definability of exponentiation. Okay, so we're going to end early today. There's just one other thing I want to say, which is how general this technique is. So what we used the beta function in this particular case to encode the sequence as I wrote down in the proof, x to the 0, x to the 1, the sequence of powers of x all the way up to x to the power of y in order to compute x to the power of y. So actually we've only used the beta function to encode sequences of this form. But the way the method worked was we could show, then using the beta function, that we could define the exponentiation function because of the definition of exponentiation, in which basically you can view the computation of an exponential as an iterative procedure, in which you start with 1 and you multiply by x a certain number of times, well, y many times, and then you get to the value of x to the power of y. And what we're using really here is that the value of x to the power of y plus 1 is defined recursively in terms of the value of x to the y and then some operation on it. So the method we used to encode exponentiation basically boils down to the fact that exponentiation is defined by a procedure that's called primitive recursion. So it uses essentially that exponentiation as what we call a primitive recursive definition. So in the case of exponentiation, this definition is that x to the 0 is 1, and then x to the power of some number larger than 0 is x. As you recursively compute x to the power, so x to the n plus 1, recursively compute x to the n, and multiply the result by x. And in fact, there's a general way of defining functions called by primitive recursion that generalizes this to any function that you can define by a similar method in which you have a base case or two, and then actually in the case of primitive recursion, one base case for 0, and then the value on a successor is defined recursively in terms of the value on the predecessor. And for any such primitive recursive definition of a function, we can again use the same approach that we characterize the sequence of iterations, or the sequence of recursive calls, if you like, but you basically calculate the function of 0, the function on 1, the function on 2. There's always a recursive step that gets you from one to the next, and you characterize that sequence, and you can then get the result. So basically, a generalization of the proof of the method shows that every primitive recursive function that has such a definition is representable by a sigma 1 formula. So it's sigma 1 representable. To do this more general result, we will actually see what it means to be a primitive recursive function. But and for those of you who did computability theory, you already know that. But in any case, we're going to need the primitive recursive functions. In the old days, I used to prove this more general result. But basically, yeah, the interesting ideas are all in the proof of the result we've had, and the method is just the natural generalization. So I no longer do that. But in any case, we will see later what primitive recursive functions are, and we'll see how. And you should be able to, if you want to work out for yourselves how to extend the method, you can think about doing that for yourselves. Okay, so that's everything I've got for today. Are there any questions before we leave? Okay, so thank you, and see you next week.